The activating electron donating group makes the ring more nucleophilic, but not at every position equally. When we do an electrophilic aromatic substitution reaction, we need to use a benzene ring as a nucleophile to attack some kind of electrophile. Now, benzene's not a very good nucleophile, that's why it needs to react with a super electrophile. I have another video, an overview of the electrophilic aromatic substitution that I'll link to down below. But one of these pi bonds will break and act as a nucleophile to attack the electrophile to do the electrophilic aromatic substitution reaction. That means one of these carbons is going to have some kind of excess electron density to act as a nucleophile in this reaction. For an unsubstituted benzene, all 6 carbons are the same, so it doesn't really matter which pi bond we use and which carbon attacks the electrophile. But what if the benzene already has a substituent on it? Now the other carbons are not the same, and it does matter which carbon we use. How do we know which carbon will be the one that attacks the electrophile in this reaction? Furthermore, does it matter what kind of functional group is attached to the benzene ring? Yes, it does. It's actually very important. The kind of group attached to the benzene ring is going to have a dramatic impact on what kinds of products we can form. Stay tuned because later in this video, I'll show you how to use the functional group on the benzene ring to predict exactly which kinds of products will form in this reaction. The most important thing we need to do in determining the regiochemistry of the electrophilic aromatic substitution reaction is to decide whether the original substituent is itself an electron withdrawing group or an electron donating group. This isn't a video on identifying electron withdrawing and donating groups. I have a separate video that I'll link to down below. But we have to identify what kind of group we're dealing with before we can figure out what the products are going to look like. The methoxy group, because it has its own lone pairs of electrons, is an electron donating group and an activator. I also have a separate video on activators and deactivators that I'll link to down below. To do the electrophilic aromatic substitution reaction, we know that the benzene ring needs to be a nucleophile. The activating electron donating group makes the ring more nucleophilic, but not at every position equally. And that's key to unlocking the regiochemistry of the EAS reaction. Yes, the ring becomes more nucleophilic, but not at every position equally. And if we can figure out how the electron density is distributed, we can figure out the regiochemistry of the reaction. The best way to do that is by drawing out the resonance contributors of our starting material. We can take the lone pair of electrons on oxygen, drop it down to form a double bond, break the carbon-carbon pi bond, and deposit those electrons locally onto carbon to draw the next resonance contributor. That puts a negative charge on the ortho position and a positive charge on the oxygen. If you need help with ortho, meta, and pair, I've got a separate video on that I'll link to down below. We can continue the resonance series by moving the negative charge sequentially around the ring. As we complete the resonance series for the electron donating group, notice we can move the negative charge to most places around the ring, but not all places around the ring. And that's where it gets really interesting. Notice the places where we can put the negative charge through resonance. Through resonance, we can put a negative charge at the ortho position and at the para position, but notice we never get the negative charge to be at the meta position. There's no valid resonance contributor for an electron donating group that puts a negative charge at the meta position. The only positions that experience an increase in electron density are the ortho positions and the para position. And that's the secret. That's the secret sauce that's going to help you figure out the regiochemistry. If the electron donating activating group makes the ring more nucleophilic, but only at the ortho and para positions, then when the ring has to be a nucleophile, it's going to preferentially be a nucleophile at the ortho and para positions because those are the positions with excess electron density thanks to the electron donating group. Because the electron donating groups activate the ortho and para positions preferentially, we say that electron donating groups tend to be ortho and para directors. So when we go to predict the products then, our products of the EAS reaction with an ortho-para director, that's an electron donating group, will have the new electrophile at either the ortho position or the para position in a ratio that's honestly hard to predict just by looking at the structures. It's not easy to predict whether the ortho or para will be the major product just by looking at the structures. By contrast, substituents that have their own pi bond, these tend to be electron withdrawing groups and they tend to be deactivators. The ring needs to act as a nucleophile. Electron withdrawing groups take electron density away from the ring and make the ring less nucleophilic, but not at every position equally. And again, like we saw before, that's going to be key to figuring out the regioselectivity of the EAS reaction. As before, we should draw the resonance contributors of the starting material to see where the electrons are distributed around the ring. I can draw a resonance contributor that breaks the pi bond in the ring, withdraws the electron density from the ring, and pushes the electron density up onto oxygen. This allows me to start drawing the resonance series. That withdraws electron density from the ring and puts a positive charge in the ring. Like before, we can move this charge around the ring, completing the resonance series. So the electron withdrawing group removes electron density from the ring, but not at every position equally. Preferentially at the ortho and para positions, we see the positive charge. These are the positions that lack further electron density. Through resonance, we get a partial positive charge at the ortho and para positions due to an electron withdrawing group. That makes the ortho and para positions less nucleophilic than we would otherwise expect. If the benzene ring has to be a nucleophile, and if the ortho and para positions are less nucleophilic than we'd otherwise expect, the only positions left to be a nucleophile are the meta positions. I want to be clear here. It's not that the electron withdrawing group makes the meta positions better nucleophiles. It's just that it makes the ortho-para positions worse nucleophiles. It's kind of a double negative. Its meta positions are the least worst nucleophiles remaining in the ring after the electron withdrawing group removes the electron density. Because the meta position is the only position left with any semblance of electron density, we call electron withdrawing groups meta-directors. With this knowledge, when a ring with an electron withdrawing group reacts in an electrophilic aromatic substitution reaction, only the meta position is able to react, and so we end up with the meta-substituted product as really the exclusive product of these reactions. And that's your big takeaway for this reaction. Electron donating groups make the ortho and para positions more nucleophilic, so when the nucleophile reacts, it reacts at the ortho and para positions preferentially with electron donating groups. With electron drawing groups, we see the opposite. We take electron density away from the ortho and para positions. The only electron density left is on the meta positions, so electron withdrawing groups tend to give the meta-substituted product. I can't end this video without talking about the one exception to everything we've just talked about, and that is halogen-substituted benzene rings. Halogens, through induction, are electron withdrawing groups and deactivators. They pull electron density out of the ring through induction and make the ring less nucleophilic. But when we look at the resonance contributors of the starting material to see where the electron density is actually located, we find something surprising. Bromine, even though it's an electron withdrawing group, has its own lone pair of electrons. So we can bring a pair of electrons down from bromine and push a negative charge onto the benzene ring. As always, we can push this negative charge around the rest of the ring. What's surprising about the halogen-substituted benzene rings is that even though it's an electron withdrawing group pulling electron density out of the ring, after it's done pulling electron density out of the ring, through resonance, we see that we still have electron density at the ortho and para positions. The ortho and para positions are still the positions with the electron density after the electron withdrawing group removes that electron density. So when the halogen-substituted benzene rings react in an electrophilic aromatic substitution reaction, even though it's an electron withdrawing group, this is the one exception where it is an ortho-para director. And with this one exception, when the halogen-substituted benzene ring reacts in the electrophilic aromatic substitution reaction, the products we see are the products that are substituted at the ortho and para positions. So even though halogens are the one exception to our rule, we can still make sense of it by drawing out the resonance contributors of our starting material. And now you have the pro tips you need to conquer your next exam.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.